Okay, welcome back. We made it to the second video. Analyticity of critical points of generalized integral Menger curvature. A few details. So I skipped over a lot of details in the first talk for the sake of brevity and just to get the ideas across. Let's do this in a bit deeper. Not much, but a bit. There's a still joint work with Nicole Ford-Obermeier. She's still doing her PhD in Salzburg, and we've been still funded by the DFG and FWF. Let's get into it. How to gain derivatives. This was the first big thing I skipped over. The second was constructing an analytic majorant. We talked about that as well. Okay, you might remember the slide. We decomposed the first variation of our energy into highest and lower order terms and had an L2 representation of these. And then I said we can show that the L plus third derivative of gamma is bounded above by the Lth derivative of the main term. And then a bit later I said that this is of course for critical gamma equal to the Lth derivative of the remainder term, and then we can bound this one above and gain derivatives. Okay, let's talk about these two things. First, this inequality. Before we can do that, we're going to need some other notion of fraction subler space than I talked about in the first part, which might be a bit more complicated because it involves Fourier analysis. If you know Fourier analysis, you're going to be bored by that. I should say this is not an introduction to Fourier analysis. This is just the tiny parts we need, and I'm by no means an expert, so this is just really the stuff we need, very simplified. Okay, let's take the Fourier coefficient first. The k Fourier coefficient or Fourier transform of gamma is just the integral over the unit interval times gamma of gamma times e to the minus 2pi kx with respect to x. And for nice gamma you can represent gamma by its Fourier coefficients, and they have another upside because if we take the Fourier transform of the Lth derivative of gamma, this is essentially the same as taking k to the L times the Fourier transform of gamma. So we have a really nice representation for derivatives. And lastly, we're going to need Parseval's relation, which just states that the L2 product of two functions is equal to the series over the inner products, complex inner products of the Fourier transforms of these functions. And with these we can define another notion of Sobolev space. Or really the same Sobolev space but with a slightly different norm. We can say that gamma is in Hm, that means m weak derivatives which are all in L2, if and only if this series here converges. And this is 1 plus k squared to the m times Fourier transform of gamma to the 2 squared. And I claim that this is another norm for the same Sobolev space. Then why is that the case? Well, let's look at the kind of boundary things. So just ignoring this k squared, we have 1 times the Fourier transform squared, and by Parseval's relation, this is the same as the L2 norm of gamma. And the other extreme is taking k to the 2m times gamma hat squared. Of course, this is k to the m times gamma hat and then parentheses squared, and this is more or less the mth derivative of gamma. Or this is the Fourier transform of the mth derivative of gamma, and so again by Parseval this is the L2 norm of the mth derivative of gamma, and so it kind of makes sense. But the nice thing here is nobody said m had to be natural, well, except for me. This series also works with any m, with any real m. So let's take positive ones because I have no idea about negative ones, but they seem to work. And this is an equivalent definition. Okay. And with that in mind, we can take a look at the formulae for the main term. So Datenreiter actually gives two versions. I'm going to work with the Fourier version because, well, we're doing Fourier analysis now. And they said the main term applied to gamma and h is equal to this thing times the Fourier transform of gamma times the Fourier transform of h. And this thing, this QPK, is actually a coefficient which goes to 0 for k to infinity, and the order of k is encoded here directly. We needed an L2 form of a main term, so let's write that on the left-hand side, and then recalling Parseval's relation, we can quite quickly work out that the Fourier transform of the L2 version of the main term has to be equal to that stuff here. So gamma QPK times k to something times the Fourier transform of gamma. And as I said, the QPK go to 0, no, not to 0, but they're constant for k to infinity. Sorry, so they're in the order of 1. Okay, that's good to know. And with these things and the definition of the subleft norm, we can actually do our estimate. So let's start. The L derivative of the L2 form of the main term squared is equal to the series, and we have here the Fourier transform of the L derivative of the main term, and we know how to deal with L derivatives in the Fourier transform. We just take k to the L times the Fourier transform of the original function, and we know the Fourier transform of the original function. It looked like that. And now we want to end up with the L plus third derivative of gamma. So we need and 2L plus 6 here, or 2 and in parentheses L plus 3. So we shift a few of these k's over here, and the rest remaining k's will go into here via this inequality that k squared to the alpha is greater or equal than 1 plus k squared to the alpha times some constant. At least if k is not 0, and if k is 0, then everything is 0, so we're okay. And then we can simplify this one to that one, and this is really just the subleft norm of gamma with the L plus third derivative of gamma. But not the HM norm, but the HM plus 3p minus 7, which is a bit more than the HM norm. Okay, this takes care of the first inequality I showed on this one slide about getting derivatives. Now we have bounded the L plus third derivative of gamma by the L derivative of the main term, and for critical gamma this is equal to the L derivative of the remainder term. So let's take a look at the remainder term. It looks like this. So Datenreiter derived this form, and it's kind of complicated. So we should probably, actually this is already the shortened form. The origin is a bit longer. So they're more capital gamma terms. Let's not go there. It's too much. Works out, but you need lots of techniques, and it's very technical, so it's too much for this talk, I guess. Let's take a simplified form. Roughly, the remainder term is the derivative of an analytic function applied to gamma prime times some products of gamma primes times some function capital gamma. And I said gamma is analytic. We have a product structure with this O times thing, and then we have gamma. And gamma is a quadruple integral over differences of gamma prime times some other differences of gamma prime divided by something that turns up in the differences. That does not look too nice. You might remember from the first talk the semi-norm I used for introducing the fractional sublet spaces. This is called the Gagliardo semi-norm. And it turns out you can bound this stuff above by it. And in the end you get that the alpha derivative of capital gamma is bounded above by the alpha's first derivative of small gamma in some slightly higher subleft norm. And the slightly higher is the reason why we needed to do the bootstrapping in the first place. So otherwise we would just get this nice recursive estimate and everything works out. So because we already talked about the bootstrapping, and in the end this kind of looks like the derivatives of gamma again, also small gamma, let's get rid of capital gamma. And then we differentiate that, and then we want to bound the norm of that. And in order to do that, here are the basic ideas you need. We're going to need the product rule, or the Leibniz rule, because it's generalized. We have multiple factors, and we have higher derivatives, and so on. And we're going to need the chain rule, again, higher derivatives and complicated stuff. And the chain rule gets ugly quite quickly. And then there's this formula called Bruno formula, which gives a general chain rule for general derivatives in one dimension. And then somewhere they called Mishkov came along and did this for functions going from R to Rm to R again. Okay. And if we have these formulae and we know that we have a triangle inequality for integrals, even if we use the HM norm, this has to do with Buchner measurability, and we have the Banach algebra property for HM, at least if m is greater than 1/2. This means that the product of f and g in the HM norm can be bounded above by the product of the norms times some constant. If you're saying, well, Banach algebra has to be constant 1, then renormalize, take the HM norm times c, everything works out. And finally, we're going to need that we can bound analytic functions even in Rm as we did in 1D, so the alpha of the derivative has to be bounded by c to the alpha plus 1 times alpha factorial. And if we have all this, we can stir a bit, and in the end it boils down to this. The alpha derivative of the main term is bounded above by this sum and this multinomial coefficient, which come from the Leibniz rule. So we have k factors, because we had k factors in our original formula, and times this one here. So this ought to be the derivative of something. So this comes from the derivatives of g prime times the derivatives of gamma prime, which are here. And this is the polynomial from Fadibun's formula. Don't worry too much about that. If you want, we can talk about that in a minute. So, and then we have a bound for R tilde. What we still need is the analytic majorant. And to talk about that, we're going to need a bit of a closer look into the generalized Fadibun formula. So, for all natural numbers L and M, there's a universal polynomial with non-negative coefficients. It's important so that we can use monotonicity, such that the alpha derivative of f applied to g is equal to this polynomial applied to the alpha derivative of f at point g of t and the jth derivative of the ith component of g. So this is just a chain rule in a very complicated setting. And of course this works for all f and g, which are differentiable enough. And with this formula we can work on. What do we want to do? Well, we want to find an analytic f such that the alpha derivative of f is equal to our upper bound for the right hand side if we plug in some function c on both sides. And if we take that c to be a solution of c dot equal to f of c of t, and if f is analytic, then c is analytic, and then I said by induction, it turns out that the L plus third derivative of c is greater or equal than the L plus third derivative of gamma, and since c is analytic, so is gamma. Okay, and how to find this analytic f? Well, we already had this upper bound. Let's define a phi by just replacing every instance of gamma by c in this formula. And then you see that we have the j plus first derivative of c everywhere, which is a bit ugly, so for the sake of simplicity, let's get rid of these plus ones. And now this kind of looks like a derivative if you look closely, because this is the derivative of something, or at least the upper bound of the derivative of something analytic. And then we have this Leibniz rule structure here, so we have the j first derivative of something times the j ith derivatives or something else. So, and this here kind of looks like the derivatives of c to the k minus 1, because we have k minus 1 factors here, and with this Leibniz form here, this works out. So we want this to be the derivative of some function a times c to the k minus 1. And this function a has to take n arguments, because we had n arguments in the Bruno formula, so this is kind of a dirty trick, and we just take the same argument over and over again. And then we call this the L plus first derivative of f. So actually we call just this thing here f. And then we're done if a is analytic and has this as a derivative. And there is an a that does that. I think you can find it in the proof of the Cauchy-Kovalevskaya theorem. And it really looks like this. We take c times 1 plus the same c times n times small c of 0, so the analytic Majorant in the end, minus the sum of the entries to the minus 2. And the nice thing is with this to the minus 2, if you differentiate it, let's say alpha times, you get an alpha factorial here. And using this c, you get a c to the alpha, then this c we have c to the alpha plus 1. So that's very nice. And then we get something that is just this one to some other power. But we only plug in c of 0. And if we plug in c of 0 for x, well, we have n times c of 0 minus n times c of 0. So this here vanishes, and we have 1 to some power, which is 1. So it works out really nicely in the end. And this a really works for any analytic function, so you just have to take the c accordingly so that you have the right bound, and then it works out really nicely. And this was the details I was going to offer. Thank you for listening to the talk, and I hope to see you at the Q&A sessions, or maybe in real life sometime, hopefully. Here, if you want to take a look at the sources, here are the most relevant for this talk. Thank you.